So what I'm going to be doing is implementing this trie data structure from scratch, and for that I need a main method. So that is right here, public static void main. Now the first thing is I need a set of strings. So I could keep that in a list. Yes, a list of strings, and I'll just call that a set of strings. That's equal to a new array index bounds. Really? So intelligent these days at IntelliJ. Okay, didn't know that. It's a list. So this set of strings will have what? P, Q, R, S. Yes, that's one of the strings it will have. Then it will also have a few other strings. So in total there are 5, and then there's P, P, R, T as a second string. So that's nice to know. So what about PSST? Yeah, we need to put that in. Next one is a little weird, I think. Yeah, QQRS. And then PQRS comes up again. So these are the set of strings that we have. And what we need to do now is perform operations. So, fine. We'll have a class called trie. Okay, and this is going to have a start node. That's all it's going to have. So it's going to have a node. So it'll be something that you can't change, just the start node. And what is a node? Well, it hasn't been defined yet, so let's do that. Class node is actually, I think I'll name this better. I think I'll name it, name the node as trie node. I don't really know if that helps, but fine. So a trie node is what we have. That's the root, in fact, of the trie. And each trie node is going to have some information. So one of the things that we want to do is keep the count of the number of strings that we have. So that would be int terminating. So this will keep the count of the strings which have terminated at this position. And another thing that we want to do is have a set of pointers. So like we said, we need to have maybe one character pointing to multiple characters, which could be its children. So we are going to have a set of characters, a set of pointers actually. So a set of trie nodes is what we have. Now, because we are constrained in this problem to just 26 characters, we have a set of 26 trie nodes. Okay, and I'll be storing that in an array. Yeah. So I just need an array of trie nodes. Can I get that? Yes, I can. Trie nodes, yes, absolutely. And then what's the length of that? Well, that is 26. No, I don't need to commit yet. Fine. And what is my trie going to have? It's going to have a start pointer. That's everything, right? Yeah. That's all that I need. In fact, we can just get rid of this. We can say that, I mean, a trie, when you're creating a trie, it should be able to create the node, the root by itself. So this is just going to be a new trie node. Yeah. That's all. So the root is initialized, everything is ready, except we need the insertions, the deletions, the updates, I'm keeping it aside for now, but insertions, deletions, and what else? Squaring should be pretty accurate. So what I'm going to do is I'm going to keep a function here called next, right? That will be telling you what is the next trie node that you need to go to in case you're searching for a character C from this node. Okay, that's what it says. So if that happens, then what I do is I return trie nodes, the pointer that you want, minus A. This is just to make sure that it doesn't exceed 26. Okay, fine. So we have one function which tells you what is the next node that you need to go to. What else? We need a public function because people are going to actually call this called count. Let's say so. That's going to give you the count. Int. What else? Query. So you need to query this trie for a particular string s. And what's going to happen is that you'll go to the point where string s, that's odd. So should query be here? No, it should be in the trie, not the trie nodes, because querying is on the tries. So fine, we have a string s. What's going to happen is, first we'll pick up the first character in this trie, that is, we go at the root. So root. Now the root is entirely empty, so it doesn't represent any character. What we need to do is go to the first character of the string. So root dot next. Let's make this public here. Root dot next for s dot char at 0. This has given you the trie node that you need to go to first, usually p in our case. But yeah, this is going to give you that trie node. So I'll just call this first. Okay, and from here, what you're going to do is you're going to go on traversing the trie till you are actually out of nodes to traverse, out of characters to go through. So you just need a for loop here, right? For, in fact, we can actually use this, and I don't need a first pointer as much. So this is what I have, and for loop is what I need. This dot length. Yep. So this is giving me the character at this position. Initially, that will be the first trie node. So what I need with this, I take the first trie node, and from there I need to go to the next trie node. So from there, not from the root, but from there. So I need some sort of a next here, right? Let's call this current, and your current is going to go to the next of the current. So initially, current needs to be initialized outside. That's going to be the very first character. That's the root is pointing to. So next s dot char at 0. The very first character from the root will give you your current pointer. Your current is going to be updated all the time by going to the next pointer, and so on and so forth. Now, if at any point you see that current is null, then you know that this string does not exist, and what you return is 0. Okay. Otherwise, if you have run out of string and you still have a current, then you return whatever the count of current is. I mean, basically the number of strings which are terminating at that point. Okay, this is the query. The query will tell you if there is no such string, it will give you 0. Otherwise, it will give you the number of strings which are terminating at that point. So I'll just make sure that this is right. Okay, or we'll write test cases and figure out. So that's query. What about insert? Insert is going to be pretty similar. So we have insert a string s, and what I need here is the very first trie node that I'm going to. Now, one case that I haven't handled is what if that character doesn't exist in the trie yet. Yeah, this is going to then throw an exception because current is going to be null. So I'll try to go to current.next. So what I should really do is put that over here. Okay, if current is null, then there's no such string and you just return 0. If it is not null, then we go to the next part that we can. Okay, this code seems more right. So, fine. Here, I'm trying to insert s. So, if the current is null, then I need to insert a node. So that would mean root.next at this point. So this is actually the trie nodes that it has, that pointer, that array of pointers. This should be pointing to a node, and that trie node is fine till now. I mean, there are no strings terminating from that, so this is fine. So if it is null, then we create the node. What else? Right, so if it is null, then we create the node. So we do this for every I in the string. Right, so this is fine. Cool. So let's understand what we have done. We have taken the current pointer and we have made it point to the place that we want it to, the first character in the string. So this should happen here. Okay, and at any point, if current is null, then we should insert a string over there. So that would be insert a trie node, basically. Current this is making a little less sense, so I'll just make this the root, right? And at the root, if the pointer where you want to go to is not existing, so this is I again, then you create the pointer. That's what's happening here. Okay, so at the root, if that node doesn't exist, I create it. Nice. Makes sense now. Makes a lot of sense now. So I don't need to go from 0 actually. I mean from 1 actually. I can just go from 0. Now, what else? This is also not required because current will set itself up. If I put 0 here, that's also fine. So the code is a little cleaner now. And what's happened is I have been able to insert and query till this point. What else can we do with this trie data structure? So another thing is current dot, the new node, that has to be set here. Current has to be updated. So current is going to be current dot next. Fine. And what else? Well, when you have reached all the nodes and you're done, basically you've finished your job, then what you do is you just increment the trie nodes, terminating at this point. Okay, queries and insertions done. Deletions are a little complicated, so I think I'll just fast forward this. In case I don't, then I'm very lucky, because I don't think I'll get this done very fast. So, but let's try. So if what I really need to do is I need to query. Okay, so the exact same code of the query will be taken here, and I don't need to return anything. But the thing is, this has to be decremented. That's really what's happening. Current, if it is null, then this string does not exist, and what I should do is throw an exception. Okay, because this string doesn't exist. What are you talking about deleting? Change, it's the delete function. The number of strings which are terminating at this point are decremented by 1 when you delete something, and that defines the delete thing. So, yeah, that's pretty much it. None of the other code has changed, thankfully. So the other thing that we need is an update function where a person specifies a string which was earlier there. So we'll call this obsolete, and we'll call the string that they want us to insert as the updated string. Right. So for the end user, the person using this trie from outside, it's going to appear as if the try changed. It magically took my string and updated to whatever I wanted it to. But what we are actually going to do is we are going to first delete the obsolete string, and then we are going to be inserting the updated string. And I think I'll try to avoid showing off any vocabulary by calling it the old string, and this will be the new string. Okay, so the update function is very simple. It just uses the insert and delete functions. Now what? Is there anything else? Oh yeah, the delete function. So I talked about actually taking the nodes which are count 0 and finding out if they don't have any children or anything. You could do that, but thinking about it a little more, the space complexity that you require for this is important, but it's going to complicate the code a lot. So I'll just leave that for now. In case there's a problem in which we face this constraint of space, that's where we can actually implement that going to the parent and deleting the child node, because it's going to complicate the code over here in the try node, where you'll be needing to have a parent pointer, and you'll also need to have which child of the parent pointer just called its delete function. So it's going to get a little complicated, so we'll just avoid it now. Okay, we have a fully functioning try right now. Or do we? We need to check that by creating it. Okay, and this is our new try. That's it, that's all it needs. So what I'm going to do is I'm going to insert each string. So this set of strings, I'm going to be inserting each string into this try. Okay, fine. And once all the strings are inserted, actually I have constructed this try entirely. So I would like to query for the count of PQRS, which should return me 2. Right? True try dot query. Yes, you're so smart, intelligent. PQRS. Yes, this is the string that I want. PQRS. Yeah. And you know what? We'll also be trying a string which doesn't exist, ABC. And we'll also be trying a string which does exist but just once. And let's comment these out so that let's just check that if it even works. Okay, we're running this. Let's just zoom in a little bit more. Yeah. Okay, there's a lot of compiling going on right now. It's a complicated piece of code, to try. It took about 70 lines to write. Oh my god, so complicated. What's it really doing? It's building for so long. Yeah, I think it's done, compilation done successfully, and we have an exception at line 112. 112? Oh yeah, 43. Yeah, I didn't out of bounds exception. So I is going out of bounds, is it? No, the try nodes. Oh, okay. So here's the issue. When we have a string, it's a set of characters, and small a is actually equal to 97 in the ASCII value. So what we need to do is wherever we are actually accessing the try nodes, this array, we need to be subtracting with small a, because that's what we are doing. I mean, that's a logical addition we need to this problem. So that's 1 place, 2 places, 3 places. Yeah, these are the only places where we are actually using them. Cool. Right. So that's it. Let's run it again. I highly doubt it will work this time, but you never know. 2. Oh wow, superb. It actually worked. But let's confirm that. And this is the genuine smile you get when your code is working. 2, 0, and 1. I can't believe it. No, okay. Not too fast now. Let's delete something. Let's delete TSST and then search for it. Okay? So try.delete. Oh god, that poor string TSST. All it did was whisper stuff. Right. So these guys are useless. I know what they are. They're 2, 0, and 1. We are interested in deleting the string and then finding out what's the count. I'm a genius actually. I actually printed out the string PSSST. Okay. This time it should work if the delete is working properly. So 0, yeah. So after deleting PSSST, PSST, it says that there's no more of that string remaining. Now if I try to delete it again, it should actually throw an exception. So of course at this point I think I'm showing off, but yeah, this also takes care of the other scenarios. That's weird. Let's go to the delete function. If current is null, okay, current is never null. So string doesn't exist, yeah. That's fine. So string doesn't exist is possible, but what we really should do is actually return 0 here. Or rather not do anything. We should just return from this point, because it's a little unnatural behavior if you have already created the string and you delete it and then you query for it, then there's no exception. No, if you already create the string and delete it again, what really happens? I think what I'm doing is I'm making it -1. Yeah. Let's confirm that. Yeah, I have a strong suspicion I'm making it -1. So that shouldn't happen, because once you've deleted, once it's hit 0, even if you delete it 10,000 times after that, a single insertion should make it count 1. So yeah, it's coming to -1. So there's a logical error here, and what we need to do is we need to check actually that if the current count for all terminating nodes at this point is 0, then we shouldn't decrement. That's it. As for if it doesn't exist, well, if it was 0, then what we can do is we can throw an exception, because that string did not exist technically and you tried to delete it. So in most coding contests, of course, you won't want this, but I'm just doing this to make sure that everything is clear. So yeah, now it should throw an exception, because it will try to delete a string which doesn't exist. Yes, there's a runtime exception on the delete function at this point, because although the nodes did exist, we saw that the count is 0, and therefore we just deleted that string. We tried to, but we couldn't. It gave us an exception. Now, insert, delete, everything works fine. In fact, that's it for the try thing. We could also try to update PSST. What we are going to do is, we have been very harsh with PSST, so we are going to be updating QQRS to PSST, and we won't be deleting this fellow. So initially, the answer that we should get for PSST is 1, and when we update QQRS to PSST, the answer for PSST is 2, and QQRS should be 0. Okay, let's just confirm that. I don't know if you can actually see this. I've been overjoyed. I haven't actually zoomed into the output. Yeah, so you see that the first result was PSST's count, which was 1. That's fine. Initially, count 1. Then QQRS after the update, this string was deleted, so it became 0, and yeah. Then when you query for PSST, because there's an insertion of PSST, basically QQRS has been converted to PSST, we get the count as 2. So this code seems to be working quite good. So before we go into the time complexity, I'll just provide you with a sample question. Chef and string is one of the questions that you can try. It's from June 2015, and well, the question could be solved using tries, but not efficiently enough, and we'll see why. But yeah, using tries, you can solve this question, and you can see that over here, I have made numerous attempts using tries, and at the end, I had to use a completely different approach, which actually got the right answer. So for 100 points, I had to use a different approach. Using tries, I could get 30 points. And in fact, let's just look at the solution. So there's a lot of hocus pocus that's happened here, and the code is dirty. But the important thing to notice is that for large test cases, everything was timing out. and had actually made sure that it's correct, but it wasn't optimal. So what was surprising me was that tries have a particular time complexity, and let's just look into that right now. If you look at this try data structure, you'll see it looks very innocent because it just contains one character, and then there is B, and then there is maybe another A over here, and then P, and this has P, Q, R. So this looks simple, right? One node, each node having one character. But we saw that in the implementation, you don't need the characters as such. What you really need is whatever properties you want for that particular node. So that's all the data that you need. Apart from that, you need a set of pointers also. Okay, and here's where things usually get very expensive, because tries, they don't store too much information, but the overhead of maintaining the pointers, about 26 pointers that we did, is very large. Okay, and each of these pointers, on the other hand, could potentially go on to 26 more pointers. Of course, you are still storing the string efficiently, but the number of pointers are really getting into the constant factor that you have. So the space complexity order L into N, this is the worst case, also has a very big constant factor, which we usually ignore because of the order analysis. That's where we ignore it. But here, we really shouldn't. We should think about maybe the space complexity is L into N into C, because this constant, each node, is taking a lot of space, mainly because of these pointers. Okay, and what ends up happening is that even if you create a small try, it might take a lot of time to traverse it, to actually construct it, to keep it in memory. These things are something that you need to take into consideration, and that's primarily the only reason why that the code wasn't working. Because if you see this try, what is the order complexity for this? When I want an element, when I want to match a string to any string in this try, so let's say the string length is L, the string with the larger length, so that is L, it's called capital L. At the absolute worst case, I'll have to traverse this try for capital L nodes till I see that there is no string which is matching, or there is a string matching. So capital L. So order L operations per query. How many inserts do you need? Order L. How many deletes do you need? I mean, how many computations do you need for an insert? Order L. How many for a delete? Order L again. And a query is order L. Now, of course, update is just an insert and a delete, so that's order L too. Okay, so you see that everything is very efficient. For n strings, when we are matching with n strings, this is giving us an order L operation. So if you have Q queries, then this is Q into L, which is actually extremely good in terms of time complexity. But because of these constant factors, tries are very often not feasible. You can't use them for these operations over here. So what else can we use? There's something called suffix arrays. Okay, and I'm not going to be going into that because that requires a separate video. But suffix arrays are the practical versions using which you can actually play with strings. Suffix arrays, essentially they just contain all the suffixes that you can. So you can have a look at that. But the important thing is tries are interesting. They might work for cases where the character set is really small. So where the constant factor is really small. Usually that means a binary try. Okay, and the binary try is just a try with alphabet size 2, which is zeros or ones, that's all. So a binary try, if the question requires that, you could think about it, you could have a go with it, because it's just a binary tree. But if it requires lots and lots of characters, you seriously need to consider this constant factor also. And the easiest way to just check it out is actually write down the code and then post it, as long as it's a long contest, because tries are very easy to implement. Like we saw, it didn't take even 100 lines. Yeah, and that completes tries. So I'll just share the code for chef and string, the try version and the not try version also. But for that, you need to have a look at something slightly different. It's called the Z function or something, yeah. Who knows? There's another algorithm which is quite interesting, which is AHO-COSAC. something like that. I really can't spell this, so I won't insult the scientists. But this algorithm lets you count the number of occurrences of a string in text, and very efficiently. But I'm not sure if I can just, get to that on the very next thing, because there's a list of stuff which I need to do, which you can of course suggest me to do. So I have this entire list, and it's so huge that I'm getting rid of problems one by one. But the speed at which I'm actually completing the problems is slower than the speed of the list increasing. So, but of course, your suggestions are welcome, and I'll love to add them to this endless list. Yeah. So, and if you want any notifications for when I do complete those problems, then you can subscribe. Yeah. Apart from that, really, the tries are all done, and I'll see you next time. Thanks.